magic. Fireworks. It's excited electrons. Today we're going to, or this evening, we are going to explain why it is we saw the colors that we saw today in lab, and why that is that all elements have their own unique emission spectra. Okay, so what you guys saw today was the same thing that Niels Bohr saw at the turn of the century that got him thinking about and led him to propose a new model of the atom, just a step more evolved than Rutherford's nuclear atom. Emission spectra is the radiation that is emitted by substances. The sun and a heated solid have a continuous spectrum. That is, all wavelengths of visible light are represented in the spectra. And when we looked at when we took our spectroscopes and we looked up at the fluorescent lights, or outside, that's what we see. We just see we see a rainbow, right? We see a continuous spectrum. So we see all of the wavelengths. We observe all of the wavelengths of visible light. But the emission spectra of atoms in the gas phase do not. Actually, they're not in the gas phase, are they? They're in the plasma phase. They produce bright lines. That shouldn't say gas, that should say plasma. They produce bright lines in different parts of the visible spectrum. Okay, and when you were looking through your spectroscopes today, you saw that. You saw those single lines at particular wavelengths. So not all wavelengths of light, visible light, were being emitted by those plasma phase elements. Okay, so line spectra, which you looked at today in the spectroscopes, are light emissions only at specific wavelengths. And every element has its own unique emission spectrum. So it's like the fingerprint of the element. It is the way that astronomers and astrophysicists can determine the composition of a star hundreds of thousands of light years away. By examining the light that's coming from the star, you can deduce the elements that make up that star. All right, so Niels Bohr wanted to know why. Okay, why is it that every element has its own unique emission spectrum? Not long after Planck and Einstein, so Planck in 1900, that energy is quantized. and Einstein that light actually has a dual nature. We can look at it as being both waves and particle-like, in that it is a stream of photons. Bohr provided an explanation. So what you saw today through spectroscopes and based on the information that came from Planck and Einstein, Bohr came up with a new and improved vision of the atom. I think that's pretty doggone amazing. He said, Bohr's model of the atom states that the single electron in a hydrogen atom could only reside in certain orbits. And I am using the word orbit here, people, on purpose. It's going to be further refined, but for now, okay, they only reside in certain orbits, and each orbit had a particular energy associated, which was fixed in value or quantized. And if you can remember back to the graphic that you did on Friday, so you drew illustrations of all the different models, or 5 different models of the atom. And what I would hope that you would remember, you could go to your notes right now and look, was that Bohr's model has got electrons orbiting at different distances from the nucleus. And so it almost looks like a target or a bullseye. The nucleus is in the center, and then in rings at different distances from the nucleus, we have got these orbits. And each orbit has a very particular energy that is associated with it. So if I go to the board, right, the Bohr model is we've got nucleus, and encircling this nucleus we have orbits of electrons, right, like bullseye. And he's saying that each one of these orbits has its own energy associated with it, in that if an electron is occupying one of these orbits, it has to have a certain amount of energy. These orbits are quantized, meaning that the electron always has to have the same amount of energy to be here, or here, or here, or here. Okay. Bohr attributed the emission of radiation by an energized hydrogen atom to there's going to be one there, I was very excited when I was typing this, to the electron dropping from a higher energy orbit to a lower one, and giving up a quantum of energy, a photon, in the form of visible light. And we're going to watch a really nifty graphic in class tomorrow that will help to illustrate this point. Right now, just get this down, and the animation speaks a million words, believe me. So, he says it's giving off a certain wavelength of light because we've got an electron that is dropping from a higher energy orbit down to a lower energy orbit, and in order to drop back down, it's going to release the energy in the form of visible light. Okay. So a little vocabulary here. Ground state is the lowest energy state for a particular electron. Excited state is higher in energy than the ground state. Okay, so a ground state electron is in the lowest possible energy state that it can be in. Excited state is any energy state that's higher than what it normally has in an atom. And finally, the brightness of a spectral line depends on how many photons of the same wavelength are emitted. All right, so this is the very first time we've talked about electrons occupying orbits of different energies. And we will get into this in great detail after the winter holiday. The important thing is that we know that Bohr came up with this idea based on information, brand new information that had come up in the scientific community about energy being quantized and that electromagnetic radiation behaves as both matter and wave, and that all elements have their own unique emission spectrum. Okay. We can also determine mathematically the amount of energy that an electron is emitting when it jumps from orbit to orbit to orbit, and that we will do